Now we've built up all the background we need to completely understand the conditions for a minimum of the norm of ax minus b. Let's first remember that if x bar is a minimum of the function, then the derivative at x bar must equal 0 in every direction. While that's a general fact, by convexity of the function we're interested in, the norm of ax minus b, the converse is also true. If the derivative is equal to 0 in every direction at a certain point, then that point is a minimizer. So the task at hand becomes finding a point such that the derivative at that point is equal to 0 in every direction. So the task is, for an arbitrary d, we need to calculate the derivative of this function which maps scalar real numbers to scalar real numbers and evaluate that derivative at t equals 0. Let's expand terms since it's the square of the norm of a vector. The square of a norm of a vector is the vector transpose times itself. This can be expanded into 4 terms by distributing the multiplication and the addition. 2 of the terms are identical and therefore they can be combined. That gives the 2 in the middle. We've used the fact that the transpose of a matrix vector product is the product of the vector transpose times the array transpose. That we derived when we considered matrix-matrix multiplication. We can further expand this by grouping together terms that don't involve t as well as terms that do involve t. We're looking to take the derivative with respect to t. Since this is just a simple quadratic function of t, the derivative is obvious. Evaluating that at t equals 0 concludes the first part of our calculation. This is a column vector d transpose to become a row vector times a column vector. Notice that there's no grouping of parentheses around the a transpose a x bar term. That's because of the associativity of multiplication. It doesn't matter how we group them, and therefore I can be sloppy about giving you a specific grouping. Remember that for x bar to be a minimum of the norm of ax minus b squared, and hence a minimum of the norm of ax minus b, it must be that this derivative is equal to 0 for all d in Rn. That takes us to a simple lemma about vectors, which I'll start by stating a very simple lemma, almost a tautology, about scalars. Suppose w is a real scalar, and it has the property that d times w equals 0 for all real numbers d. Then I claim it must be that w was actually 0. That's obvious, but let's write the proof. Well, if w isn't 0, then choose a particular d, namely d equals w. Clearly, d times w is w squared. Since w isn't 0, that's greater than 0. So therefore, this w does not have the aforementioned property. There is a d in R such that dw is not equal to 0. Therefore, if the aforementioned property does hold, it must be that w is equal to 0. Let's make a similar statement about vectors. Suppose w is an n by 1 vector, and it has the property that d transpose w is equal to 0 for every possible d. Then I claim it must be that w is the 0 vector. The proof is very similar. If w isn't the 0 vector, then choose a particular vector d, namely d equals w. Clearly, d transpose w is w transpose w, and since w is not the 0 vector, that's greater than 0. So therefore, w does not have the aforementioned property because there is a d such that d transpose w isn't 0. So let's go back to the condition we were looking at. We know that for x bar to be a minimum of the norm of ax minus b, it must be that this expression, d transpose 2a transpose a x bar minus 2a transpose b, must equal 0 for all d in Rn. We can now apply the lemma. If x bar is a minimum of the norm of ax minus b, then for every d in Rn, this quantity must equal 0. That gives that the derivative at that point is 0 in every possible direction, which we know is a characterization of the minimum for convex functions. There also is the lemma we just proved. Notice that 2A transpose AX bar minus 2A transpose B is playing the role of W. X bar must be such that that vector W has the property that D transpose W is equal to 0 for all possible D. That implies that the W vector, 2A transpose AX bar minus 2A transpose B, must equal 0. This is the characterization of X bars that minimize the norm of AX minus B. This can be rearranged by canceling the 2's and moving one term to the other side into the following equation, which is often written as this. Let's summarize. If X bar achieves a minimum of the norm of AX minus B, it must be that A transpose A times X bar is A transpose B. Remember that A was n by m and B was n by 1. Therefore, the dimensions of this linear system of equations are as given. This is a square system of linear inequations, and we know it always has at least one solution, because the norm of AX minus B always has at least one minimizer. It might have infinite solutions depending on A. The graph of the norm of AX minus B might be a trough where the minimum value is achieved over an infinite line, or in higher dimensions a plane, or in higher dimensions some generalized plane. Moreover, because of convexity of the function norm of AX minus B, every solution of these equations, which guarantee that the derivative is equal to 0 in every direction, minimizes the least squares objective. The zero derivative condition is equivalent to being a minimizer. Hence, this provides one approach to solving the linear least squares problem by reducing it to a square system of linear equations that have the property that there always is a solution, and in fact may be many. Given that we're limited to one module on least squares, that is an appropriate place to stop with the theoretical development. You now understand what system of linear equations exactly characterizes the minimizers. The algorithms you'll use generally don't solve the problem this way and use more sophisticated techniques, but theoretically they're equivalent to this. As you pursue more courses in linear algebra and numerical methods, you can learn more about efficient and reliable solutions to least squares problems.